Welcome to the 14.5 lecture on curvature, normal vectors, and torsion. This is a very long section. I have 64 lecture slides on this. There should probably be 2 sections, and I'll break this video up into 2 parts. So we begin with curvature. Before that, though, this uses the unit tangent vector. Recall that the unit tangent vector of a smooth vector function r of t is its velocity, r prime of t, over the magnitude of that velocity, and that just makes it a unit vector in the direction in which it is going. And curvature. So that R describes a smooth parameterized surface curve. S denotes the arc length, and T is a unit tangent vector. Then the curvature, which we use kappa for, that guy is the Greek letter kappa, is the magnitude of the t ds, where t is the unit tangent vector. So here's an illustration. So we are parameterizing by arc length, and remember that that means that we're moving along at a speed of 1 unit a second along this curve. And in this area, the curvature is high because the rate of change of the unit tangent vector is large around this point. While in this curve, the curvature is smaller because that rate of change in the unit tangent vector, as you can see here, is smaller, small curvature. So you might think, wait, curvature sounds kind of like the derivative. In a way it is, but the derivative is with respect to an intrinsic orientation. So like you might have a parabola and you have a derivative of that. But if we tilt that parabola sideways in some sense, like this, then the corresponding point might be here when we tilt it sideways. And then the derivative here is very much different from the derivative here. But curvature does not care about the orientation of the curve in space. It only looks locally at the curve and is an intrinsic sense of, well, how quickly that curve is changing direction, regardless of its placement. And note, so this is intrinsically with an arc length parameterization. And as we saw last time, arc length parameterizations are in practice impossible to find unless the speed already happens to be constant. But not to worry, we can find an equivalent formula for this that does not require an arc length parameterization. So we have that the curvature kappa at a point S, where S is that arc length parameterization, is the magnitude of dt ds. But we need to find a usable formula for this to compute the same thing, since we can't find arc length parameterizations in general. How can we do this? The chain rule. So dt ds is, by the chain rule, the same as dt d little t ds. One way to think about this is that the little dt's cancel out, and you're left with the big T ds. And both of these guys are much more reasonable to find. D big T, d little t, that is the just derivative of the unit tangent vector with respect to whatever our original parameterization is. And d little t ds is a scalar function, so we can use the fact that the magnitude of c v is the magnitude of c times the magnitude of v, like that. This is a scalar function because s is a scalar and so is t. They're both just real numbers. So the result is that this is just a real number. So we can separate it out like that. But now d little t ds, that's odd looking, but it's the reciprocal of ds dt. And ds dt, that is the rate of change of arc length as a function of time. But what is that but the speed? The speed is the rate of change of arc length as a function of time. It's how quickly your magnitude is changing. So ds dt is speed, which is the magnitude of velocity, i.e. the magnitude of r prime of t. So d little t ds is the same as 1 over ds d little t, and that guy down there, and the magnitude is the speed. And look at that. That is a usable formula to find the curvature. So this is our practical formula, and this is what we will always use in practice to find the curvature, unless we happen to already have an arc length parameterization. But even in that case, then that means that the speed is 1, and this is just as fast to find or compute, essentially. Yep, so these two forms are equivalent. D big T, D little t is T prime, and V is R prime. Okay, and that is kappa of S, but really we should say kappa of T, since the right-hand side is T. So this is just the slide from the textbook saying the same thing, that kappa of T is what we just found. So let's do an example, and this example will double as a theorem. Let's find the curvature at any point early on a circle of radius r. So a circle of radius r at the origin, or centered at the origin, is parameterized by r of t is r cosine t, comma r sine t. Recall from earlier sections that the unit circle that was r of t is cosine t sine t. So if we scale both of those by r, then it will just scale the whole thing out by r, and it will make it of radius r now. So now we want the speed. That's one of the two components that we want. And that's the magnitude of r prime. Derivative of cosine is minus sine, and of sine is cosine. And we wind up with that. We can factor out the r squared, and we wind up with our usual sine squared plus cosine squared. And the speed is the magnitude of r. We can assume r is positive because it's the radius. Okay, so the speed is r. And what else do we need? What is t? The unit tangent vector. That is the derivative, which is the direction and speed over its own magnitude to make it of unit length. That's the same as v over the magnitude of v. We just found the magnitude of v, and v is that derivative that we found here. So we have minus r sine t, comma r cosine t all over r. And we wind up with minus sine t cosine t is the unit tangent vector. Okay, so now that we have those, we now need to take the derivative of t and then take the magnitude of that. Okay, so we found that, and now we need to find t prime. T prime, the derivative of this is minus cosine t, comma minus sine t, and then the magnitude of t prime is, okay, we'll wind up with our usual sine squared plus cosine squared. So that's 1. Okay, so kappa of t at any t is equal to magnitude of t prime of t over the magnitude of v, which is 1 over r. And notice that all the t's always canceled out, so this is regardless of what that input t is. Okay, and to be more mathematically precise, I should have put in of t in equations like that, but in practice, we sometimes don't write them. So long as we're clear on what we mean, that they're functions of the parameter. So that's both an example, and it shows this theorem that a circle of radius r has constant curvature of 1 over r. And the fact that a circle of radius r has this constant curvature of 1 over r gives a nice alternate visualization of curvature. To find the curvature of a curve here C at a given point, say P, we find a circle tangent to the curve whose second derivative there is also equal to the second derivative of the curve. So it's not only tangent, but also it locally looks like that curve in the sense that its second derivative is also equal to the second derivative there. So it's like double tangent in a sense. If you find such a circle that fits smoothly along the curve at the point P, and you take its radius, then the curvature of the curve at that point is 1 over that radius. So skipping ahead a few slides, ignore this for now. Just look at this picture. So here's a parabola, and to visualize the curvature, so around this point, the vertex, it looked kind of pointy, as it says here. It's turning around quickly, and the circle that fits snugly there is of small radius. That's a small r, and what that means is that here, 1 over r, the curvature, well, we're dividing by a smaller number, so that means that the curvature is larger. While up here, then the curve is not curving very fast at all. We have a very big R if we were to extend this, going out. And then the curvature there, which is 1 over that big R, smaller. So another example, here's a curve. Do you recognize what kind of curve this curve is? Take a moment and think about that. What do you think this traces out? Well, we can rearrange this into this form. This is of the form R0 plus TV. That is a straight line. A straight line never turns around at all, so it should have curvature 0. Let's show this. And to show this, we won't need to go through everything. Let's find t here first here. So the unit tangent vector at a given point, that's r prime over the magnitude of r prime, is abc over the square root of a squared plus b squared plus c squared. And then t prime of t is 0 because the unit tangent vector is constant. We're taking the derivative of a constant in all components. And that means that this guy is equal to 0. So the numerator is 0. So therefore, the curvature is just always 0. So we have found that circles of radius r have a constant curvature of kappa equals 1 over r, and lines have a constant curvature of kappa equals 0. But how does this jive with our understanding of the curvature being 1 over the radius of the circle that rests snugly against the curve? Okay, here's a line. What kind of circle rests snugly against this curve? Certainly not that one. Pretend that's a circle, not that one. Not that one. But as these circles get larger and larger, then you can see they seem to be resting more and more snugly. Okay, very big circle. And finally, so the radius of the circle r needs to go to infinity to rest snugly against the line. And thus kappa will be 1 over r is 1 over infinity is 0. Very roughly. This isn't mathematically precise. Mathematical precision would require limits and the like, but hopefully it gives a good geometric understanding. And in this sense, so does this mean that lines are like circles of infinite radius? Fun thing to think about. That's kind of true. A line is like a circle of infinite radius. Now, here's an important thing that we'll be using. The unit tangent vector t and its derivative t prime are orthogonal. We'll call this t prime after normalizing it, the normal vector to the curve. For now, though, let's just show this. So we want to show that t dot t prime is 0. That's the meaning of orthogonality, recall. And recall that for any vector u dot u means the magnitude of u squared, just expanding this out algebraically. And thus t dot t, well, remember that t is of unit length. That means that it is a unit vector. So its magnitude squared is 1 squared, which is 1. And then taking the derivative of both sides and applying the product rule, we learned the product rule applies to dot products as well. So this is t dot t prime plus t prime dot t, and the derivative of 1 is 0. These two things are the same, that's 2t dot t prime. And then dividing both sides by 2, we have t dot t prime is 0. Thus, t and t prime are orthogonal. Notice that this would not be the case if we had used just any parallel vector. We had to use specifically the unit parallel vector so that this was constantly 1. And this type of property is a very useful algebraic corollary of us always normalizing to unit vectors. And we'll see a number of more examples of utilizing this. Now, the formula that we learned and have applied here for curvature is nice in a lot of contexts, but it does involve first finding the unit tangent vector. Typically that will involve dividing by, well, it divides by the magnitude, which often has a square root of some of the squares. And then you need to find the derivative of that for t prime. So in many cases, it can get algebraically very messy. And for that reason, we want an alternate formula for it that we can use with less algebraic hassle. So first, note that t of t, unit tangent vector, by definition is r prime over the magnitude of r prime, which is v over the magnitude of v, velocity over speed. And therefore, multiplying both sides by the speed, moving it over there, we have that v of t is equal to t times the magnitude of v. Now, acceleration, by definition, is dv dt, but we just saw that v is this guy. And then by the product rule, that's the derivative of the first part times the second part plus the first part times the derivative of the second part. Now, some of this looks like rabbit out of a hat mathematics in the sense that they seem to be pulling things like this out of nowhere, but it's certainly going somewhere. Now, v cross a. So this guy is v, again by up here. And a, as we just saw, is this whole guy. And the cross product distributes. So we distribute it over both components. And the first component, that times that cross that, is actually 0. And why is that? Well, the first part, vt, and the second part, ddt of the magnitude of v, t, those are both scalar multiples of the same thing. So those are parallel. They are both scalar multiples of t. And parallelity means that the cross product is 0. So thank goodness, because that looks pretty ugly, but it is just 0 and it goes away. So we wind up with a much simpler cross product that is this. Now, in this, we take the magnitude of both sides, and now magnitude of v cross a is the magnitude of that guy. That's where we begin here. And now we apply the geometric definition of the cross product. Recall that the magnitude of u cross v is magnitude u, magnitude v, sine theta. And this is where we use what we just proved. Recall that we just showed that t and t prime are orthogonal. So the picture looks like this. There is t prime is orthogonal, and thus we have an angle like pi over 2, and the sine of pi over 2 is 1. So that's why that guy is 1. I know at this point you might be thinking, okay, this proof is going on a long time. The reason I'm presenting it is that it highlights so much geometry and understanding of what we've been doing, which I believe is very important to understand. Even if you couldn't, of course, do this proof on your own, I think it's very instructive to understand why things like this are true. Okay, now things begin to look nice. So that guy is 1. And also, this magnitude of t guy is 1, since t was a unit vector. So that guy also goes away. So we're left with just magnitude of v times magnitude of v is magnitude of v squared, and this dt dt. And finally, we recall our definition of the curvature as being dt dt over magnitude of v. This was what we applied when we found the curvature of a circle. And multiplying both sides of this equation by v, we wind up with this. So this is where we finally put our kappa in there, and we wind up with a very nice formula for curvature. So this guy is kappa v by just multiplying both sides of this equation by magnitude of v. And therefore, the magnitude of v cross a is this magnitude of v squared times that guy is kappa magnitude of v. So kappa times magnitude of v cubed, from combining those two parts. And then dividing both sides by the magnitude of v cubed, we finally have our alternate definition of curvature. So that's a pretty amazing mathematical derivation and proof. It utilized so much of what we've learned and is quite clever. And you might be looking at this and wondering, wait a moment, it has a cross product in it. Isn't that algebraically worse? In many cases it might be, but in this case it's definitely not, because this original definition that we had been using, again, t was the unit tangent vector that already has typically a dividing by a square root of sum of squares to normalize it, making it of unit length. And then we take the derivative of that. So we have a derivative of a reciprocal of a square root of sum of squares in general. And that is not nice to do. We don't want to have to differentiate a reciprocal of square root of sum of squares. So this is much nicer. It is way nicer to just find the velocity, the first derivative, find the second derivative, acceleration, take the cross product, and then take the magnitude. There's way less horrific differentiation here. So that's our big theorem on our alternate curvature formula that is often much nicer to apply. Let's do an example. Let's find the curvature of y equals e to the x. Let's just visualize the picture. At 0, 1. And to find that curvature, we first need to parameterize it. A nice way to parameterize it, kind of the default way, is to just let x be t. So we let x be t, and that's x, that's now y, which is equal to e to the x, but x is now t, so that's e to the t. And we have this z coordinate of 0. Why do we have that? Aren't we working on the xy plane? Well, because we will be using the cross product, and the cross product needs 3 dimensions. It is only defined for vectors in R3. Yeah, so all that does is we're considering this curve in the xy plane, and we have this z axis coming out of it, but this curve is still on the xy plane, and its z coordinate is just always 0 because it's on the xy plane in 3D space. That's all that's saying. Okay, so we do not want to use the original formula, because then when we differentiate, we would have a 1 and e to the t in the denominator. So this guy has components of v and a. Let's find v and a. Okay, so v, that's r prime, is 1 e to the t. Derivative of t is 1, derivative of e to the t is itself, and a of t is 0 e to the t. Okay, now in this guy, we have 2 components, b cross a and magnitude of v cubed. Let's find the easier one first. The magnitude of v, that is the square root of 1 squared plus e to the t squared, which is the square root of 1 plus e to the 2t using exponentiation laws. And the magnitude of v cubed is then this guy cubed. And we want to write this in the following way. Okay, so square root, that is the same as to the power of 1/2. And then we're cubing that. And now product rules again. 1/2 times 3 is 3/2. So that's the same as an exponent of 3/2. So this guy here is that denominator. And now we want b cross a. We want to take the magnitude of this after. Let's find b cross a first, though. So that was 1 e to the t 0 cross 0 e to the t 0. And that's the determinant of 1 e to the t 0, 0 e to the t 0, and ijk. And this gets back to my earlier comment. The reason that we needed to add this z component of 0 was to take this cross product. Otherwise, it makes no sense. But the xy plane, that just means that z is always 0. Okay, and now we go through this determinant. So we have I times e to the t times 0 minus 0 times e to the t is 0i minus j. The submatrix there is 1 times 0 minus 0 times 1. And k, we have 1 times e to the t minus e to the t times 0 is e to the t. So that's the same as 0, 0, e to the t is our cross product. And then the magnitude of the cross product. Okay, if we want to write it out like this, we can. But that's just 0. We have the square root of a square, and e to the t is always positive. So it's just e to the t. Okay, so now we found the numerator, and we already found that denominator. So now we're good to go. We have found that the curvature kappa is e to the t, and over that denominator was 1 plus e to the 2t to the power of 3/2 is what we found. Okay, and again, technically, if we want to be mathematically precise, that's kappa of t. The curvature changes as a function of the parameter t. Okay, now let's just do a little check and see what the curvature is at some particular points. So at t equals 0, this is kappa of 0 is, okay, so we have e to the 0 is 1 over 1 plus 1 to the 3/2 is 2 to the 3/2. So we have 2 to the negative 3/2 is the curvature when t is 0, and at t equals 0, remember that t was x. So that's the curvature there. And as t approaches infinity, then kappa of t approaches, okay, so we have e to the t, and down here we have e to the 2t to the power of 3/2. That's like e to the 3t. So it's like e to the t over e to the 3t. That approaches 0. And you can do this more rigorously with L'Hopital and the like, but it's 0. And that makes sense because this curve e to the t, so it's definitely bending around here, but as we approach infinity, then it's just shooting up faster and faster and becoming straighter and straighter. So because the e to the t curve is becoming straighter and straighter, that means that the curvature is getting smaller and smaller as we approach infinity. And same in the other direction. As we approach infinity this way, going to the negative direction, then the curve is obviously flattening out as it becomes more and more tangent to the x-axis. So that checks out. And that's the general curvature at any point t. Oh, and I want to point out that if we want to find the curvature only at a particular point, instead of in general, so over here we did in general for any t, if we want to find it only at a particular point, then we don't need to find it in general first. We can just plug in that particular point to begin with into the formula, and it is much nicer to compute. Okay, so here, b of 0, that's our prime of 0, which is, okay, so we have 1, 2t, 0, evaluated at 0 using that notation, which is 1, 0, 0. Yep, so r prime, we took the derivative of this, it's that, and we're plugging in 0. And that means that the magnitude of b of 0 is 1, and so is its cube, still 1. Okay, so the point is that guy there is 1 at 0, at t equals 0. And a of 0, that would be 0, 2, 0, evaluated at 0, again taking the general second derivative of this guy, and then plugging in 0. There is no t here, so when you plug in 0, you get back 0, 2, 0. And then v of 0 cross a of 0, that means 1, 0, 0 cross 0, 2, 0. And the point is, well, one point is that this is a much nicer cross product to compute because it has so many things 0. And there is no t, since we are considering it only at a single point. So that's 1, 0, 0, 0, 2, 0, I, j, k. Okay, I, we have 0, 0, 0, I. J is also going to be 0, and k has a coefficient of 2, being the various determinants of the submatrices. Okay, and then the magnitude of V of 0 cross A of 0, that is the magnitude of 0, 0, 2 that we just found, is 2. Okay, and that guy, that is that numerator there. So the curvature at 0 is 2 over 1 is 2. And now let us recall our geometric understanding of curvature in terms of circles. So that 2, that means that if this is the curve y equals x squared that we just did, then specifically, what is this radius? We had that the curvature there was 2. So that means that the radius of the corresponding circle, that's 1 over kappa, is 1/2. So if you find a circle that rests snugly against the parabola at the vertex, for this parabola y equals x squared, then the radius of that circle is going to be 1/2. That's the unique circle, the unique radius of the circle that rests snugly against the parabola at the vertex.